Good morning, students. Welcome to Microwave Engineering Laboratory. And today's experiment is attenuation measurements. And last experiment we seen microwave frequency and wavelength measurement. And today's experiment is attenuation measurements. Coming to the aim. So the aim of the experiment is to study insertion loss and attenuation of an attenuator. And the required operators is the first one, microwave source, klystron tube, isolator, frequency meter, variable attenuator, slotted line, tunable probe, detector, mount. And match determination, test attenuator. Here, there are two attenuators we have to use in the laboratory to perform this experiment. The first type is a fixed one, and second type is variable attenuator. And a klystron power supply with a mount, cooling fan, cables, voltage standing wave ratio measurement equipment, and as well as a cathode ray oscilloscope. Let's see the block diagram. So microwave source is connected to the isolator to the frequency meter to variable attenuator to the slotted section to detector mount, and detector mount is connected to CRO, and other side attenuator to the matched termination. So this is what the setup bench required for the required to do this experiment in the laboratory. So initially there is a klystron power supply, and it incorporates different sections. One is a modulation section, another one is display section. So a modulation section contains two knobs, bias voltage knob and a rippler voltage knob. By varying the bias voltage knob in the clockwise direction, we can fix the voltage, input voltage to the mount. And that voltage should be in between 230 volts to 240. Voltage in between 230 volts to 240. Remember that one, it is a important point. And next, after applying the voltage to a mount, when you energize the mount by applying the voltage, beam voltage, and mount fires the electron, and we know there is a electron movement that creates the current, electromagnetic wave energy. So mount creates the electromagnetic energy, and that energy which is travel towards to the isolator section. So here the purpose of the isolator is it forward the energy into only one direction, that is towards to the frequency meter side. Okay, by rotating this frequency meter, we can fix the particular frequency to a energy, and that was created by the mount or microwave source. So here we are using the X-band, and that frequency band is the starting value is 8.22, ending value is 12.4. So in between, we have to allot a particular frequency to this microwave energy generated by the source. So next, energy passes towards to the variable attenuator side, and variable attenuator to slotted section to the detector mount to the CRO or VSWR meter. So here there are two steps. Step number one, we have to perform this experiment by using the variable attenuator. Okay, variable attenuator consists of one micro scale. Okay, by rotating the micrometer, and we have to apply the attenuation to the signal. See, so here, so after reaching the frequency meter, and microwave energy passes towards to the variable attenuator, and variable attenuator has a variable attenuator has a particular micro scale like this. So by rotating this micrometer, we have to apply the attenuation like this. When you block the variable attenuator, whatever the energy reaches here, it completely blocked and travel towards to the source side. So here, initially the readings start at 25 and signal down to 0. I mean reading down to 0. So initially the value is 25. So when you rotating the meter, okay, first value is 25, means there is no attenuation. We haven't applied any attenuation to the signal. And 25 down to 20, 20 to 15, 15, 12, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Like that when you down the scale. So when you apply, when you make it to 0, I mean completely, when you completely block the variable attenuator and whatever the energy reaches here, it's completely take the diversion and travel towards to the source side. So that's how you have to perform the experiment. I mean step number 1 by using the variable attenuator. So whenever we are taking, whenever we are rotating, so that corresponding reading you have to observe in CRO. Okay, I mean signal strength we have to observe it CRO. Then step number 2 is we have to perform the experiment, the same experiment by using the fixed attenuator. There are different types of fixed attenuators are available in the laboratory. The first one 3 dB attenuator, and second thing is 6 dB attenuator, and third one is a 10 dB type of attenuator. Suppose if you chose the 3 dB attenuator, when you connect the 3 dB attenuator to the setup, so after connecting the 3 dB attenuator, you have to calculate the signal strength by using the CRO. So initially we have taken the signal strength without the attenuator, that is V1. Okay, without attenuator. So whatever we see in the signal strength on the CRO, maximum signal strength, that is V1 without attenuator. After connecting the attenuator, so we have to take the values of the microwave frequency. That value is V2. So signal strength without attenuator is V1. Signal strength with attenuator after connecting the attenuator is V2. Then perform the 10 log of P1 by P2. I mean in terms of powers, then you will get the attenuation value. Otherwise, if you are using the only voltage readings, then take 20 log of V1 by V2, then you will get the attenuation value. So by taking the attenuation value, then that value should match whatever the fixed attenuator you used here. Suppose, so if you using the 3 dB attenuator, so whatever we practically find, that value is which is equal to the 3 dB. Suppose if you take the 6 dB or 5 dB and whatever the ratio we have calculated, that value is matches to the 5 dB or 6 dB. Then 10 dB also like that. So this is how we have to perform the experiment, attenuation measurement experiment in the laboratory. Then two steps we have to perform. Let's coming to the formula for attenuation. It is a two-port bidirectional device which attenuates the microwave energy which is flowing through the waveguides. Okay, the formula for the attenuation is A in dB, which is equal to 10 log of P1 by P2. I have given the formula here in terms of powers, so we can perform this one in terms of voltages also. That is attenuation in dB, which is equal to 20 log of V1 by V2. Okay, then see, coming to the observations, see here. So there is a microwave meter readings. So when you performing the variable attenuator experiment, so you should take the values 25 down to 0. Okay, 25 down to 0. Then P1 is without attenuator, P2 is with attenuator. So take the readings, corresponding readings here, then find out the attenuation. So after find out the attenuation, so the expected graph be like this. Okay, take the microwave meter readings here and attenuation values in y-axis. X-axis microwave meter readings and y-axis it is a attenuation values. Then graph be like this. Okay. So this is how you have to perform the experiment in the laboratory. And coming to the Viva questions for this experiment, the first question is what is attenuation? And the second question is how many types of attenuators we are using in the laboratory? And three, what is the insertion loss? Fourth one, what is the minimum value of insertion loss? And fifth question is, what are the methods used for measuring the attenuation? And sixth one, what are the methods used for measuring the insertion loss? So these are the 6 questions I have raised here. Answer these 6 questions. Let us move to the laboratory and perform this experiment practically. And again, I'll explain the calculations on board. Okay, thank you. Let's move to the laboratory. Welcome back to the microwave engineering laboratory. Last session, we see VI characteristics of gun diode, and today's session, let's learn about attenuation measurements. First of all, when you are in the laboratory, initially you have to switch on the fan. So switch on the cooling fan. When you are dealing the microwave test bench, make sure the air flow towards to the Klystron mount or not. Then afterwards, switch on the Klystron power supply. Klystron power supply is a solid state regulated power supply, and it incorporates different sections. The first one is modulation section, and second one is display section. Okay, then display board, then beam voltage and repair voltage knobs, and modulation knobs. Initially, step number 1, you have to select the modulation section as a amplitude modulation, and by varying the beam voltage knob, fix the beam voltage in between 230 volts to 240. 230 to 240. In between, keep any value and make sure the signal, have you getting a signal or not. And by rotating the display section knob, write down the beam current, corresponding beam current, and that beam current should not exceed 18 microamps. Initially, you have to write down the beam voltage, and that should be in between 230 to 240 volts. Then next, select the beam selection at current position and write down the corresponding current reading value, and that should not exceed 18 microamps. Then select the display section to the repeller by rotating the repeller voltage knob. Fix the signal at oscilloscope max. By rotating the repeller voltage knob, fix the maximum signal at display section CRO. Now apply voltage, repeller power supply. Give the power supply to the Klystron mount. Mount to isolator, isolator to variable attenuator, and variable attenuator to frequency meter, and at last detector mount to CRO. So this is what the block diagram or setup for the microwave attenuation measurements. So initially, Klystron mount, so by giving the voltage to a Klystron mount, and mount fires the electron into a tube. When there is a movement in the electrons, that representing charge movement, when the charge is moving through the transmission line, so obviously there is a generation of microwave energy, and the energy is moving towards to the isolator, and here the purpose of isolator is which redirects the entire energy in a only particular direction, I mean towards to the attenuator. So the purpose of attenuator, we know attenuator. So attenuator is a passive device which attenuates the RF signal. I mean when the energy is passing through the structure, it absorbs the energy and it decreases the which slow downs the microwave energy, means which attenuates the RF signal, and third energy reaches to the frequency meter. So by rotating the frequency meter, we can fix a particular frequency to a energy, and finally microwave energy reaches to a detector mount. And here the detector mount, by using a detector mount, you can detect the signal, I mean in form of square wave. Okay. So here there are 3 steps. Step number 1, just take down the input power. So we go attenuator. So attenuator, there are 2 types: variable attenuator and fixed attenuator. Let's do the experiment by using the variable attenuator now. Initially, fix the or assign a particular frequency to a energy. So by rotating the frequency meter slowly, the frequency meter values start at 8.2 to 12.4. This is what the microwave band, 8.2 to 12.4. By rotating the frequency meter slowly, we can fix the frequency to this microwave energy. So when you are rotating the frequency meter at a particular value, you will notice a dip in the signal. So just rotate the knob or frequency meter slowly and see the or observe the dip. So by rotating the frequency meter, we can assign a frequency, right? Yeah, see the dip. So this is what the required frequency. Got it right? So now we assign a frequency to the energy, microwave energy, and third value is 9.68. So this is what exact frequency is assigned to a energy. Now keep it the signal as it is. Take down the power readings, input power. Step number 2, by rotating the variable attenuator, and it has a scale, and that scale down to 25 to 0. The maximum value is 25 and minimum value is 0. So scale down to 25 to 0. By rotating the variable attenuator, just see the signal how it's behaving. So when you applying a attenuation means when you blocking the energy. So energy is traveling from source mount to towards to the isolator to the variable attenuator, frequency meter, and at last detector. So when you try to block the energy, how the signal is behaving means if the signal strength is increasing or decreasing, you have to check it. So slowly by applying load or attenuation, just check the values. See, there is no change in the signal strength. So here the value is 15. Variable attenuator reading is 15, but still there is no change in the signal strength. Keep on rotate. At a particular instant, you will observe the change in the signal strength. Okay. Now we reach 10, but still there is no change. Check it here. Now the value is the value is 6. So there is a loss of strength, right? Still, rotate it. You can observe very clearly strength is decreasing. When you blocking the energy, so there is no energy flow towards to the detector side, right? So that's why we are seeing the lack of signal strength is decreasing. Check it. So when you doing or when you perform this experiment, you have to write down the readings of variable attenuator. So we can perform the graph. So when I apply a complete load, so there is no signal at all. So entire energy reflects and flow towards to the source side. So there is no energy travel towards to the detector side. So just release the attenuator, variable attenuator, and again check it. See, so when you are releasing it, so you can see the signal strength or increasing of signal strength. So this is what we call it like the function of how the attenuator functions. So it is a passive device which reduces the RF signal strength or which regulates the power levels in a waveguide structures. So this is a step number 2. Step number 3, you have to perform the same experiment by allowing the maximum energy towards to the detector mount. Okay, so connect a fixed attenuator and how the signal behaves. Step number 3, you have to perform the same experiment by using the fixed attenuator. So previously we have done the experiment by using the variable attenuator, and we seen how the signal strength is how the signal is varying. I mean signal strength is increasing or decreasing. Step number 3, you have to perform the same experiment by using the variable attenuator. See, after connecting the variable attenuator, you have to take down the reading, I mean output voltage. The next, find out the attenuation by using a formula 10 log of voltage without attenuator to voltage with attenuator, then you will get the value, and that value is equal to whatever the attenuator we have used here. Suppose if you use the 3 dB attenuator, so after taking the ratio between the voltages, I mean without attenuator and with attenuator, whatever the value you will get, and that value which is equal to the whatever the attenuator we are using here. So that is what the theme of the experiment. Hello students, let's see attenuation measurements calculation part here. So there are two parts here. The first one, we have to calculate the attenuation for the 3 dB fixed attenuator. Practically we have taken the values. Beam voltage is 240 volts, beam current is 18 milliamps, Rippler voltage is minus 201, and output voltage without attenuator. So we perform experiment in two ways. First part, output voltage without attenuator, the value is 0.7 volts. That we have to consider as a V1. Next, in the second step, output voltage with attenuator, and that value is 0.4. We have to take it like a V2. And now attenuation in dBs, that is 20 log of V1 to V2. So 20 log of 0.7 volts to 0.4, the value is 2.98. So which is nearly equal to 3 dB, right? So we use 3 dB attenuator, fixed attenuator. So finally we proved the attenuation value which is equal to 3 dB. Then case number 2, for a variable attenuator, and take the readings. When you rotating the micrometer, I mean variable attenuator, and it has a micrometer, readings 25 down to 0. At the 25 value, micrometer reading at 25, then the attenuation value is, I mean power value is 0.7 volts. That is what the maximum power we got without attenuator. I mean what I am trying to say is, when you fix the variable attenuator at a maximum position, okay, I mean when you free the variable attenuator, so we are not applying any attenuation, that situation voltage is 0.7 volts. Then when you try to apply a attenuation to a signal, okay, or when you are applying a load, means 25, then after 24, 23, 22, 20, like that, when you rotating the variable attenuator and applying the load, the value up to 9, there is no variation in the voltage, means there is no attenuation at the signal. So same signal strength you will observe. So up to 9, there is no change in the signal strength. After at 8 also, it is a 0.7 volts only. But when you see exactly at 6, that is a 0.6. At 5, micrometer reading at 5, you see the value is, a voltage value is, output voltage value is 0.4, at 3, 0.3, 0.2, 0.1 and 0. Means when you applying a load, it stops the signal, right? So I'll show how the signal strength is decreasing by draw a graph. See the graph now. So I am taking the voltage in x-axis and micrometer readings in y-axis. See the graph clearly. Y-axis micrometer readings 25 down to 0. 0, 1, 2, 3 and so on 15, 20, 25. Other side x-axis I have taken the voltage readings in millivolts. The maximum voltage is 0.7 volts, right? So for convenience I have converted those values to millivolts. So 100 millivolts, 200, 300 millivolts, 400, 500, 600, 700 and 1000. So at the reading of 25 we got the value 0.7, I mean 700 millivolts. And next up to 7 it's the same, right? So at the reading of 20, 0.7, at the reading of 15 also 0.7, and at the reading of 7, 0.7. But 6, that value is 0.6 volts, I mean 600 millivolts, 5, 500 millivolts, 4, 400, 3, 300, 2, 200, 100, 0 means. So at the reading of 25 means when you free it up, there is a maximum signal strength, means no attenuation condition exists. When you apply in the load up to 7, there is no change, but when it starts blocking the energy, signal strength is reducing. There the maximum attenuation will appear. So that is how you have to perform in the laboratory. Thank you so much.